Since all of our other equations of motion have had a rotational version with their rotational quantities in place of the linear ones, we expect that we should be able to write a version of Newton's second law that describes rotational motion. A push or pull that tends to rotate something should induce an angular acceleration. We find that this is exactly the relationship that is correct. And the mass to use is the moment of inertia. So the version of Newton's second law for rotating objects is that the sum of all torques equals the moment of inertia of that object multiplied by its angular acceleration. So when we have a net torque, the object's rotation rate will begin to speed up or slow down. Let's look at how we might apply this to a very simple problem. Let's say I have a rotating object with an axis at center. I'm told that this object is a disk with a radius of 10 centimeters and a total mass of 4 kilograms. Around the edge of this cylinder at a radius of r is wrapped a string, and that string pulls with a force of 5 newtons. The center is fixed, so the disk is not going to move to the left with the force, but the force will cause a torque and cause this thing to rotate. So the question then is, can we calculate the angular acceleration of this disk? Well, looking at Newton's second law for rotation, in order to calculate the angular acceleration, we need to know the moment of inertia, and we also need to know the sum of all torques. So every torque comes from some certain force, and there's only 2 forces that get applied to this disk. There's the 5 Newton external pull, and there's the force of support at the axle, which is actually a type of normal force. Of those 2, the normal force at the axle can't cause any torque because it's applied at the point of rotation. It has an R value of 0. The 5 Newton force can apply a positive torque. It tends to rotate the disk counterclockwise. So based on what's been given to us, the sum of all torques is a positive 5 Newton force acting perpendicular to a 10 centimeter radius. This means I'm going to get a net torque here of 0.5 Newton meters. All right, 10 centimeters is 0.1 meters, so 0.1 times 5 is 0.5 Newton meters of torque. For the moment of inertia, I need to look at what shape it is, how large it is, and how heavy it is. It's a disk, so my factor is 1/2. The mass is 4 kilograms, and that radius is 0.01 meters squared. So 0.01 squared gives us 0.001. 4 divided by 2 gives us 2. So we're talking about a moment of inertia of 0.02 kilogram meters squared. Now that I know the total torque and the moment of inertia, I can just divide the torque by the inertia to get the angular acceleration. So 0.5 Newton meters over 0.02 kilogram meters squared. So can we do this division without a calculator? I think we can. Dividing by 0.002 is the same as dividing by 2 and multiplying by 100. So I would have 0.25 multiplied by 100 This would give me an angular acceleration of 25 meters. Let's check on the units too then. Newtons times meters. Let's go up here. Newtons times meters over kilograms meters squared. That's what we've got. So a Newton is equal to a kilogram meter per second squared. Okay, so then the kilograms cancels, and we get 1 over second squared. And since we're dealing with angular quantities, we know we can always replace 1 by radians. So what we get here is 25 radians per second per second. That's an angular acceleration, and that would be the angular acceleration of this disk. Okay, so that's a very basic application of Newton's second law for rotation with just one torque and just one object. And as we know from our work in previous chapters, that usually Newton's law is applied in situations where there's more than one force or more than one object or both. So we are going to have to recall, when we approach these rotating object problems, we're going to have to recall all of the things that we learned about forces, what the forces are, how is the tension, what are the rules for tension, what are the rules for normal force, what are the rules for springs. We're going to have to recall all those, and then in addition, we're going to have to think about where on the object are they applied, and will they cause any torque. The other thing that we had a lot of in dealing with Newton's laws problems is when there are constraints, an object stuck to a surface, or stuck on a slope, or moving in a circular path, or something like that. Those are also things we'll have to handle. So let's show a more complicated example where a couple of those issues pop up. All right, so here's a very simple example. I've got a wheel here. I'm going to label its mass as m1 and its moment of inertia as I1. I'm going to support it from its axle with a string. So we'll call this string have a tension T1, and wrapped around this wheel is another string which goes down to a mass m2 that's hanging. We'll call the radius of the wheel R1. So all the subscript 1s will go with the wheel, and all subscripts 2 will go with mass 2. So we have things that can move here, and we have things that can rotate. So let's first think about the forces involved. All right, so for object 1, which is the wheel, we have 3 forces. We have T1 is pulling up, T2 is pulling down, right? And gravity pulls down on the center of mass. So all those forces are in the vertical direction. So if there's any acceleration for the center of mass of this pulley, it will be in the vertical direction also. Let's look at object 2 for its forces. Object 2 is the hanging block here. It has a force of tension. T2 pulls it up, and M2G pulls it down, and that gives us M2A2. Okay, so that's the linear forces. That's stuff we already talked about a while ago. Now let's go ahead and look at the torques. So the only object here that can rotate is the wheel. And does it experience any torques? Yes, it does. So it's got T1 pulling on the center. That doesn't generate a torque. It's got gravity, again, pulls on the center of mass. That doesn't generate a torque. T2, however, pulls on the edge, so that does generate a torque. It pulls perpendicular to the radius at the point where it's applied, right there at the edge. And T2 pulls in a clockwise direction. So that's the only torque, so that will be equal to the moment of inertia of the disk times its angular acceleration. Okay, so those are Newton's laws. Now we do have some constraints here. We have two strings. We have T1 and T2. So we should come up with two constraints that keep this system having the strings at constant length. So for the first constraint, let's keep it simple here. Let's say that this string T1 holds the pulley at rest. So that means that due to T1, A1 equals 0, right? The other string here, T2, is a little bit harder to figure out its equation of constraint. But what T2 has is a length from here to here, and it's wrapped around the cylinder a bit more. So let's imagine here that the cylinder rotated one full revolution. So the cylinder changes its angle in the positive direction. If it were to do this by 2 pi radians all the way around, then the string would be wrapped up by 1 circumference more of the cylinder. So the change in length of the string would go, the string would get shorter by 2 pi r. Okay, just thinking about how the string would get pulled up. So that means if the disk rotates counterclockwise, then the mass must move up. And I can relate these velocities. So if L is the length of the string, L getting shorter means that mass 2 moves up. So that means a change in the y-coordinate of object 2 is equal to 2 pi, is equal to basically, so our delta angle was 2 pi, so it's equal to r times the change in angle. Okay, so that makes sense. Yeah, if it rotates 2 pi, then this moves up a whole circumference. If it rotates pi, then this moves up by half a circumference. So this is a constraint equation for the string at T2, and it means that due to T2, we're going to have A2 equals to R times alpha 1. So I can just do this. Displacements will be proportional to velocities, will be proportional to accelerations. For constraints, that's fine. So here are my 5 equations that I would now need to put together to solve for any desired quantity in this system. Let's actually put these together now. See what we can get. Put in some of our information here and simplify a bit. So A1 was said to be 0. So that means equation 1 is basically just going to give us T1 equals T2 plus M1G. All right, we'll leave that one alone for now. Okay, so the second equation tells us that T2 is equal to M2A2 plus M2G. Then we'll use the third equation here. The third equation we can use for also for T2. T2 will be negative I1 over R1 times alpha 1. Right? Equation 4 is trivial. That one we're not going to rewrite again. We've already used it in simplifying equation 1. And finally, equation 5 we'll write as alpha 1 equals A2 over R. Oh, this R should be R1, right? Yeah. Okay. So let's pretend here now that we want to solve maybe for the acceleration A2 of this mass 2. Okay, so we'll eliminate A1 out of there. So if I put together equations 2 and 3 and 5, then what do I get? I'll get minus I1 over R1. Alpha 1 is A2 over R1, so I'll have over R1 squared. That's basically this side of equation 2. That's the expression for T2 from equation 3. So that'll be there, and then I'll have M2 A2 plus M2 G. So if I want to solve this for A2, I will just basically switch the moment of inertia term over to one side with the A2, put all the A2s on the same side. When I do that, I'm going to end up with minus m2g on the other side, right? If I subtract this over there and add this one over there, this is what I get. So then this equation is what you could solve for the acceleration of object 2. So what do we get from this? Just a few comments. We get acceleration that's negative, mass 2 falls down, and the acceleration is some fraction of g, right? It doesn't accelerate downwards at exactly g. It's m2 divided by the sum of m2 and the moment of inertia over r1 squared. So again, it looks like we've got this force factor here due to m2g, and this inertia factor here depends on m2 because it's got inertia to move out of its own, and also it depends on the moment of inertia of the wheel. So the wheel has to move too, and that makes it behave as if it's a little bit harder to accelerate than just mass 2 falling on its own. Now let's do a more interesting example that I would probably consider to be a complete solution to a situation that we've seen before. It's something rolling down a inclined slope with a constant angle. But now with our knowledge of rotational motion, we're going to combine that with our knowledge of friction to really solve what actually happens in this scenario. Just from experience, we know that if you let something that's round, if you let it go on a slope, it will roll down the slope if the slope is flat. But if the slope is very steep, like an 85-degree angle or something, and you let this object go to roll, it's just going to slide down, right? It's not going to take its time to start rolling all the way down the ramp. And as it slides, it may start to spin somewhat. So it's actually a pretty complicated physical situation, and we'll be able to solve it using our Newton's second law for rotation. So let's look at the setup here. It's an inclined plane of angle theta with an object on it of radius r, mass m, and moment of inertia I. Now let's think about what forces might act on this. Well, we've got a gravitational force, that's for sure. We have a normal force, which is still applied perpendicular to the surface. And then we also have a frictional force. Now the frictional force here is it's not obvious what direction the frictional force points, but it's going to be parallel to the surface. So let's set up an axis for our coordinate system. We'll let x point down the ramp and y point perpendicular to the ramp, away from the ramp. This way, if the object rolls down the hill, it will have a positive x acceleration. In this coordinate system, our angular velocity would be counterclockwise. Now, rolling down the hill is going to mean this thing rolls clockwise, so we'll expect our values for omega to be negative. So what we'll do for the frictional force here is we'll just assume that the frictional force is in the positive x direction. We'll just assume that. And then if the math leads us towards the negative value of the frictional force number, then we'll know that it actually pointed up the ramp. That's fine. So we can always assume a direction and then find out its sign later on via the math. So let's write down our equations for motion here. Actually, before I write down the equations for motion, I'm going to redraw this diagram, with the axes x and y in a vertical and horizontal orientation. All right, we normally do this so that we can not mess up our sines and cosines for the components. Okay, so this y direction is still perpendicularly away from the ramp, so this is where the normal force points. The frictional force we assumed would point in the positive x direction, and then the gravitational force is between x positive and y negative, so it points in this direction somewhat. If I look at the angles here, this angle is similar to this angle there, so here is the angle theta. All right, so that's my force diagram. When I draw the force diagrams, all the vectors just add up normally. So my sum of forces in the x direction will be Ff, force of friction, whatever that comes out to, plus mg, and this component here, for the x component, that's opposite, so that's going to be a sine theta, and that will be equal to m ax. All right, for the y direction then, we've got normal force up. Component of gravity points down. It's the vertical component, mg cosine theta, and that equals may. All right, and lastly, our new ingredient, we have the sum of torques. All right, so gravity acts on the center of mass, so it doesn't cause a torque. Normal force acts on the at a point on the radius, but it always points inwards, right, towards the center of the circle because it's perpendicular to the circumference. So the normal force also causes no torque. So only this force of friction causes torque, and it looks like it's going to cause a, if this force of friction was indeed positive in the direction of the arrow, it would cause the object to rotate in a counterclockwise direction. So we'll have a positive torque, radius times f of f, and that will equal the moment of inertia, which I'm going to leave as a variable, times the angular acceleration alpha. So those are the three equations that we get from Newton's laws of translation and rotation. Now we've got to think about our constraints in this situation, and there's one constraint that's always there, and that is due to the normal force. Due to the normal force, the y component of acceleration is 0. All right. Now the other one that could cause a force of constraint is the force of friction. But the force of friction depends on whether this object is in static rolling or if it's slipping. Okay? So if it's slipping or sliding at the current instant of time, then the force of friction is a kinetic friction, and there's no constraint there. So if the object is slipping, then the force of friction is going to be equal to mu k, the coefficient of kinetic friction, times the normal force. And the direction for the force of friction depends on whether the object is moving down the ramp or up the ramp. So moving down the ramp would produce a positive x component of velocity. Moving up the ramp would make the x component of the velocity negative. But that's not the only thing that's going on here, because this object is also rotating. So remember that when slipping happens, it's not just always opposing the motion, it is opposing the relative motion, right? The relative motion. So we really need to look at the two surfaces here and what their relative motion is to decide whether this object is slipping or not, and what direction the object is going to feel that frictional force. So let's zoom in right on this bottom of the circle here and think about what's going on right there. So here we have a surface which has no velocity at all. And then we've got the edge of this round object that's touching right here. And at this point, we're talking about a velocity for the point that's on the circumference of this disk or round object. So it's going to have two reasons to be moving, right? If the object was just completely sliding with no rotation at all, just slipping straight down the ramp and rigidly all at rest, there would be a contribution from Vx. So Vx if it was just sliding all together. On the other hand, if it was at rest for its center of mass, but rotating with an angular velocity omega, then this point on the disk or round object would be zooming around in a circular path. So it would have a second contribution plus omega r. All right, so that is the velocity of a point on the circumference of this disk as it slides or moves down the ramp with the velocity Vx and possibly rotates at the same time with a velocity omega r. This is the same thing that we ended up with when we talked about something rolling along a surface, right? Same thing, rolling along a surface. Okay. Now, if this velocity value is positive, that means points on the edge of the disk are sliding past the surface in this direction. So the frictional force on the disk is then going to be opposite to that in its direction. Its magnitude will still be mu kn if it's sliding, but the frictional force will be in opposite direction. Right? If the velocity on a point on the circle is in the opposite direction, then the frictional force will point down the ramp. So our sign here is what matters. The magnitude is mu kn, and the direction of the frictional force is equal to the sign of this quantity, Vx plus omega r, and it's equal to that, the sign of that in the opposite direction. Okay, so if if Vx plus omega r is positive, then the force of friction is in the negative x direction. Okay, so that's the case of slipping. The other case is static rolling. In static rolling, there's no slippage between these points of contact. The angular velocity and the linear velocity are linked together in some way. And we can tell actually what that constraint is going to be by thinking about what we just did here. So Vt is the point on the edge of the round object, and the surface has a velocity of 0. So if it's rolling in a static contact, this velocity of a point on the tangential edge of the round object must be 0 too, right? So this has to match. The two surfaces where they're touching have the same velocity. That's static contact. So this means that Vx plus omega r equals 0, and then we'll have a force of friction which is equal to any possible value to maintain this constraint, but less than a maximum value mu s times n. So the absolute value of the force of friction has a limit at mu s times n. Okay, that's the basic setup of this problem. So now let's go through the math and solve. All right. First, let's label these 1, 2, 3, 4, 5, and 6. Those are 6 things that we can use. Let's look at equation 2 first. From equation 2, I get n equals mg cosine theta. This is actually 2 and 4 combined. So 2 and 4 are used up. And this is the formula for the normal force, independent of what the friction is doing. That's good. Okay, second thing we'll do is let's look at the condition of static rolling. This one is going to be a bit easier to handle. So for static rolling, if we take the derivative of this equation with respect to time, which we're always allowed to do if it equals 0, Vx is going to give us the x component of the acceleration when it's differentiated, and when we differentiate omega, the angular velocity with respect to time, we get the angular acceleration. So here from equation 6, we see that alpha is equal to negative ax over r. That's that negative sign we expected, right, for counterclockwise versus clockwise rolling. Okay, so we've used up equation 6 there under the case of static rolling. Now we'll put this in equation 3. That says the radius times the force of friction equals the moment of inertia times the angular acceleration. So this will become negative I times ax over r. And so this tells me in order to maintain the static rolling constraint, the force of friction must be equal to negative I ax over r squared. So there we've used up 5. No, we haven't used 5 at all yet. We're not touching slipping. We've used up 3 to get this equation for FF. Finally, we'll use equation 1 and plug in this formula for the force of friction. So minus I ax over r squared plus mg sine theta equals max. All right, so that's something we can now solve for the acceleration. So ax equals mg sine theta divided by m plus moment of inertia over radius squared. Okay, so we'll put this down as our solution in the case of static rolling. So if we assume that it's in static rolling, then this is how much it accelerates. And this looks pretty much like what we would expect. We get the normal acceleration, g sine theta, that we would get for something sliding down a ramp, except it's divided by an increased denominator because of the moment of inertia, contributing some inertia to make it roll. Okay, so that's the prediction for the acceleration under the assumption of static rolling, but we're not quite done with the static rolling case just yet because we have to address whether or not the static friction force is above its maximum limit. So let's go back and solve explicitly for the force of friction required. It's a static friction in this case, and see if it's actually less than the coefficient of static friction times the normal force. So we had F of F, force of friction, is minus I over r squared times the x component of the acceleration. The x component of the acceleration we solved for down here, so we'll plug that in. mg sine theta divided by m plus I over r squared. Okay, and we'll just put this all together here. We'll put absolute value signs around both sides, and we'll set up the inequality. Mu s times n, and our normal force n was mg cosine theta. Okay, so what happens here is the mg's in the numerator occur on both sides, so those can be erased. All right, so here we go. We'll do one more simplification. We've got a denominator of I here, so this is the same as 1 plus mr squared over moment of inertia. Okay, so there's our condition on the angle of the ramp related to the mass and moment of inertia of the object on whether it will be able to stay in static rolling or not. Notice what's going on here. The mu s times 1 plus some stuff, mu s times 1 without the other stuff would have just been the result if it was something sliding down the ramp with no rolling at all. Just a block sitting on the ramp trying to slide or not. That would just be mu s there. So what does the moment of inertia do here? If the moment of inertia is large compared to mr squared, then this term is small, right? And it's close to 1. So if something is really hard to rotate, then it acts similar to just a block or a non-rotating object sitting on the incline trying to slide. If the moment of inertia is pretty small, like for a disk or something where it's 1/2 mr squared, then this is going to make this thing in parentheses much bigger, and it's going to be much easier for that object to move down the incline without skidding. So this stuff here was for static rolling. Now let's rewrite the equations that we had from before so we can go on to the case of slipping. Okay, so in the case of slipping, the linear acceleration ax and the angular acceleration alpha are not related to each other at all. They're unrelated. So what we can do is just take our formula for the friction and plug it in. What I'm going to do is I'm going to write this as plus or minus here. And note that the plus case would be for Vx plus omega r less than 0. So that means, Vx plus omega r less than 0. And the minus case would be Vx plus omega r greater than 0. So let's write this as minus Vx divided by r on both sides. And that will be our scenario. So depending on how it's currently rotating, the force of friction might be in one direction or the other. So then let's solve. There's not really much to do here in terms of solving a system. We just use the first line here to get the acceleration x component. This will be g sine theta, dividing both by m. Okay, so g sine theta plus or minus mu k g cosine theta. All right, so the mu k is there from that, the plus or minus is there from that, the normal force is there. This was a not nx, that was times the sine of stuff. So mu k n is mg cosine theta, and I divided both sides by m. So this is our formula for the acceleration in the x direction. All right, then the angular acceleration alpha, this we can just solve from the third line here, r times the force of friction over I, the moment of inertia. And so this is going to be plus or minus r over I times mu k n, and m is mg cosine theta. Okay, so what do we see here? Well, we've got still this plus or minus sign, right? So if the angular velocity basically is too low, right? This is our threshold value here, minus Vx over r. If angular velocity is too low, this value is already negative, so this means the angular velocity is much more negative than it needs to be for static rolling. So it's, rolling around, it's much more negative. So it's rolling around this way quite a lot, and this angular acceleration then is going to be positive, which is a counterclockwise acceleration, so it's going to slow down until it gets to static rolling. In this case, the angular velocity is bigger than it needs to be for static rolling, so it's kind of rolling so much that it's rotating in the counterclockwise direction, so it's going to get a grip on that surface there and try to pull itself up the ramp, actually. So if this sign is minus from an angular velocity that's too positive, too counterclockwise to be static, the angular acceleration will slow down. We'll get a minus sign there. The linear acceleration could actually become negative. That rotational motion could get a grip on the surface and propel this thing up the ramp. Okay, so that's the basic solution here for that scenario. Remember, the scenario we were doing is a object of mass m, moment of inertia I, radius r. Not specified what any values are. It's set on a inclined plane of angle theta with any instant initial value of angular velocity and any instantaneous initial value of linear velocity. So the basic conclusion for this system is it can roll down the ramp just fine. Easier to roll down the ramp if the moment of inertia is smaller. If it begins with the angular velocity or linear velocity in such a way that it's slipping, then it will slide. the rotation and the linear motion will not be related, but they will approach each other. They will approach each other until they get to the static rolling condition, and then it will start rolling for the rest of the time. Okay. So finishing this example, I do want to emphasize that, this isn't like a super important process or anything. I definitely wouldn't waste any brain space memorizing the formulas that we've written on the board here. But we do go through it as practice of how to apply Newton's laws of linear motion, Newton's laws of rotation, at the same time, while there are forces present that that we've seen before, like friction, static friction, normal force, forces with constraints, and how all those simple pieces can come together to give you this quite a nice mathematical description of how something actually rolls down a surface where it can slip or roll or not.